This video explores how definite integrals work, blending visual intuition with rigorous mathematical understanding. Integrals are essential across physics, economics, and engineering, turning rates of change into meaningful totals. You'll learn to interpret the integral symbol, approximate areas with Riemann sums, and apply the fundamental theorem of calculus. We'll slice the region under a curve into rectangles, shrink their width towards 0 to get exact area, then use the fundamental theorem to evaluate quickly. Let's work through it on the diagram. What does this strange stretched sus symbol actually mean? The integral is one of the most powerful ideas in mathematics. It turns rates into totals, speed into distance, flow into volume, probability density into chance. Students often memorize integration rules without seeing the picture. But the real meaning lives in a beautiful geometric idea: accumulated area under a curve, goals. Build intuition with Riemann sums. Define the integral as a limit, then compute one exactly. Step 1. Approximate the area by slicing the interval into n rectangles of width delta x. Start with 4 wide rectangles. Each one's height comes from the curve. The sum of their areas is about 14.2. Close, but the staircase clearly misses pieces of the region. Now 10 thinner rectangles. The error shrinks visibly. With 40 slices, the rectangles hug the curve almost perfectly. The sum approaches 21, the true area. What if we let the number of rectangles go to infinity? Step 2. As n goes to infinity, the sum becomes the integral. The discrete sum smoothly becomes a continuous integral. The integral sign is a stretched s. It stands for sum. And dx is an infinitesimal width, the limit of delta x. The fundamental theorem says, pick any antiderivative f, evaluate at the endpoints, and subtract. Differentiation and integration are inverse operations. Let's use this on a concrete example. Step 3. Let's compute a clean example and verify it geometrically. Switch to a linear function where we can see the answer as a trapezoid. An antiderivative of 2x plus 1 is x squared plus x. Evaluating at 3 minus at 0 gives 12. Geometric check. The shaded region is a trapezoid with parallel sides 1 and 7 and width 3. Half times 8 times 3 equals 12. Perfect match. The definite integral equals 12. Integrals show up everywhere. Distance from speed, work from force, probability from density. One idea, endless applications. Whenever you need to accumulate a varying quantity, distance from speed, volume from cross-section, total from density, you're looking at a definite integral. Picture rectangles shrinking to 0 width. Then use the fundamental theorem to evaluate instantly with an antiderivative. The integral from a to b of f equals capital F of b minus capital F of a. One elegant formula linking area, accumulation, and antiderivatives.